So as we're finishing up the subject of kinematics, we have relative motion, relative velocity, relative acceleration. We dealt with some relative velocity problems last time, so I wanted to move ahead and look at a little more complicated one, and one that incorporates acceleration for relative acceleration. So we've got this example here. We have an intersection, maybe in a highway, and we have car A up here that's going to the left at 3 feet per second squared, so it's accelerating. We'll be told about its velocity in a moment, but that's car A accelerating away from the intersection. And then we have car B down here going around this curve, and the curve is defined with a radius of curvature of 440, and that's a little bit hard to read, so we've got 440 feet there for the radius of curvature for that thing. And at the instant we're looking at, that's 30 degrees from the horizontal or this line across there. Horizontal is a little deceiving because we're looking at a top view of this. And we're told that the velocity of car B is 30 miles per hour, and it's going to be in that direction. So the tangential direction, that's the velocity of B. So it's also moving away from the intersection, and it's a constant value. So with that, we could say, of course, that the constant means that the acceleration of B is equal to 0, right? Constant acceleration. And I should probably modify that a little bit, the acceleration of B in the tangential direction. It would, by virtue of moving around that corner, of course, have a normal acceleration, so we'll have to account for that. So we're told to find the velocity and acceleration that car B appears to have to an observer in car A. So we'd like the velocity of car B with respect to car A. And we're asked to do this at the instant when car A has reached 45 miles per hour. Well, the first thing that I'd like to do in going through this problem is get some consistent units. We've got distances of feet, and we have distances or rates of miles or miles per hour, so I probably need to be very careful with that. So if I take the velocity of car A at 45 miles per hour, and I multiply that by 5,280 feet in a mile, and 3,600, then I divide by 3,600 seconds in an hour, gives me 66 feet per second. So that's the velocity in feet per second. I'll do the same thing for the velocity of B. The velocity of car B is 30 miles per hour. I'll multiply by this 5,280 divided by 3,600, because 5,280 feet in a mile, 3,600 seconds in an hour, and I come up with 44 feet per second. I think on the first day of class I mentioned that 60 miles per hour was 88 feet per second, so that makes sense. Well, let's see if we can make this work out. I think our equation, we could say that the velocity of B in terms of a vector equation is going to be equal to the velocity of A plus the velocity of B with respect to A. Will that work? The velocity of B is equal to the velocity of A plus the velocity of B with respect to A. I think that should work. So if we look at this from a triangle or a geometry standpoint, the velocity of A, car A, is moving away from the intersection at that's that 45 miles per hour. So let me put that down. There is the velocity of A, like that, moving away from the intersection. And if I want to talk about the velocity of B, that's going to be in the tangential direction. I didn't do a very good job of showing that, but that's in the tangential direction there. So there is the velocity of B, like that. And then I could put this vector in here, the velocity of B with respect to A. Does this observe our vector expression up here? If I take the velocity of A, this vector, and add it tip to tail to this one, the velocity of B with respect to A, I get the velocity of B, don't I? Well, let me work on the geometry here just a little bit more. If I were to extend this velocity of B up here, that's going to be perpendicular or at right angles with our radius of curvature, which we are told is at 30 degrees. So that angle in there is 30. So that would leave this angle at 60, right? Okay, so this one, if that's 30, this is 60. So what do I have for an angle in there? 60 degrees, right? A lot of you can probably look at that and come up with that quicker, but that's probably the geometry I would go through to prove that to myself. Let me put an angle in here just so we can talk about this. I'll say this is theta. I've drawn this that looks like a right angle down there, but I wouldn't take that as a right angle. It probably is not a right angle. So going through this, I can talk about the magnitude. I mean, I know that the velocity of A, we had a number for that, didn't we? 66. And we had a number for the velocity of B, 44. So I've got two sides in the included angle. Looks like a job for the law of cosines. So we could say the magnitude of the velocity of B with respect to A would be equal to the square root of, what are we going to have? The square root of 66 squared plus 44 squared minus 2 times 66 times 44 times the cosine of the angle, 60 degrees. When the smoke clears on that math, that'll come up at 58.2 feet per second. Which seems reasonable looking at the relative values of the other pieces. I think we're probably okay with that. We should probably get a direction. Well, this is a magnitude. If I get theta and get a direction so I can use the law of sines, I can say that the sine of 60 is to the velocity of B with respect to A, as the sine of theta is to the velocity of B. We had the velocity of B was 44. We found the magnitude of B with respect to A, 58.2. So we could solve then and say that theta going through that is 40.9 degrees. Now, if you look at the hitting the inverse sine button on your calculator, remember you're going to have a complement of that, so you're going to have, 180 less that. But if you try to add that to 60, you'd have a real funny-looking triangle. So we can be pretty confident in that answer there. So you can put that in Cartesian form if you want to, but for our purposes, we've got the magnitude, we've got the angle. I think we've got the velocity piece taken care of. But we do need to move on to the acceleration piece. But before we do that, are there questions? Well, we'll move ahead then. I'll try and leave a little bit of this here. So, see if this works for a little while. So if we talk about the acceleration, if I were to differentiate the velocity equation, we had the velocity of B was equal to the velocity of A plus the velocity of B with respect to A. I could say likewise that the acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A, just differentiating the velocity equation that I started with on the first part. And we said that, maybe we'll inventory what we have here. We've got that the acceleration of B in the tangential direction is equal to 0. That comes from constant velocity. But we said that B is still accelerating by virtue of going around that corner. So we know that the acceleration of B in the normal direction, that's going to be v squared divided by rho, the radius of curvature, isn't it? So what did I come up with for velocity? 44 feet per second. Square that. I divide by the radius of curvature, that was that 440 feet, and we come up with 4.40 feet per second squared. Okay. I guess I got a 4 that looks like a 9 there, don't I? So 4.4 feet per second squared. So I'm ready to look at a triangle. We know that car A is accelerating away from the intersection, so that's pretty easy. There's the acceleration of A away from the intersection. And we know that car B, while it's not accelerating the tangential direction, I mean, this would be a lot tougher problem if it was accelerating the tangential direction. We'll talk about that in a moment. but it is accelerating in the normal direction, so that's going to be going right back up that line that's depicting the radius of curvature. So I have then, there is the acceleration of b, which is really the acceleration of b in the tangential direction, which takes on a value of 4.4. And then over here, I have the acceleration of b with respect to a. Does that stand up to our vector equation? If I take the acceleration of a and add it to b with respect to a, that gives me b, doesn't it? What was my acceleration of a? I think I was just flat told in the opening statement that is 3 feet per second squared. Feet per second squared. Feet per second squared. We okay with that thus far? Well, this, yes? Acceleration of, oh yeah, I've got the acceleration of b in the tangential is 0, and the acceleration of, yes. So the question is I messed up here, didn't I? This should have a subscript of what? N. Thank you very much. Okay, so we get enough subscripts in there. There we go. Thank you. Because indeed the acceleration of the tangential is 0. And that's probably worth talking about at this point. That's a good segue, thank you. Is had we had tangential acceleration in that, had the car not only been going around the curve, but speeding up or slowing down as it went around the curve, we would have a tangential piece in there too, wouldn't we? So now we'd have a four-sided figure. What do you think about working with four-sided figures? No fun, right? Okay, so in that case, you're probably going to come back to the vector equation and just work through the vector math. But if you can get it into a three-sided figure, it's probably a little easier to work with the geometry. So let's finish this thing up. And I think this angle here, that's going to be that 30 degrees again, isn't it? And maybe I'll put one more angle here. I'll say that this is beta. And we could say again that we have two sides in the included angle, so I could talk about the magnitude of the acceleration of b with respect to a. And that would be the square root of, using the law of cosines, 3 squared plus 4.4 squared minus 2 times 3 times 4.4 times the cosine of the included angle, 30 degrees. So this turns out to be equal to 2.34 feet per second squared. So that's the magnitude of the acceleration. I should probably get the direction. I can do that with beta. So I could say that 4.4 divided by the sine of beta is equal to 2.34. That's what we just found, right? 2.34 divided by the sine of 30, the angle opposite it. And we'd come up with beta. I think your calculator would probably give you, what, 69.8. Why don't we just call it 70? Okay. If you go through that, I suspect your calculator, a lot of your calculators will give you 70 degrees. What do you think about that answer? It may not be right. We should probably say, or we should have 110 degrees. That satisfies this equation. It is then up to us to figure out which one satisfies that physical situation. Now in the velocity, it was fairly easy because I had a triangle where the complement added to the existing angle would have gone past 180 degrees. But I could take either one of these and add it to 30 and still have room for this small angle up there, right? So it's a little more difficult. So what I could do, I mean, this is a classic problem, and it's a great problem to get students to give the wrong answer, which hopefully is done for learning purposes. But let's go over here. I'm going to carefully segregate this off, and I'm going to say, what if? What if? What if that happened to be a right angle? If beta was a right angle, and I had then 3 here, and we'll go ahead and take our 2.34 here, and we know the Pythagoras says that this would be 2.34 squared plus 3 squared. which when you go through the math on that, I think I got that number there, 3.8. 3.8. And we recognize that 3.8 is less than 4.4. So what's our conclusion? So beta is what? Less than 90 degrees, is that right? No, or did I get that wrong? Greater than. Yeah, greater than. Good thing I got this warmed up here. Okay. So beta has to be greater than 90. So now with this equation and coming back and looking at this, I know my answer for beta is 110 degrees. Okay? So we go through the same process. It's just not quite as clean or as easy. Questions with that? Like I said, this would be a little uglier problem if the acceleration in the tangential was not equal to 0. I probably wouldn't use geometry on it. I would go back and put in my vector pieces. You'd get something like this. The acceleration of b in the tangential direction plus the acceleration of b in the normal direction is equal to the acceleration of a. Maybe a is going around a corner, right? We could really make this ugly. Acceleration of a in the tangential plus the acceleration of a in the normal plus the acceleration of b with respect to a. So I've just expanded these two terms to account for those possibly going around the corner. In that case, you're going to have a figure that's got, what, 1, 2, 3, 4, 5, 6 sides, 6 being the answer to this. I don't want to mess with that, so I would just carefully fill in these pieces and go through a vector solution. Questions with that? So that's a good relative velocity, relative acceleration problem. The next and final area in Chapter 12 dealing with relative motion is a class of problems where they're hooked together with a chain or cable or rope or something like that. And there's a trick to solving these. I don't like to use the term trick, but it describes it pretty well. And that's accounting for the length of the rope or the cable or the chain that is attaching them together. So let's say that I've got a couple of boxes or crates here. Crate A that is maybe moving to the right. And if crate A is moving to the right, I think by looking at this scenario, you'd recognize that crate B would be moving down. Now, they're probably not going at the same rate. That's often the question. Given the velocity of B, what's the velocity of A? Or given the velocity of A, what is the velocity of B? So our task is to come up with that. And like I said, the trick or the tool is probably a better name, but the trick is to look at the length of that rope or cable. So I could say that the length is going to be x, that gets me that much of it, plus as it goes around that pulley, that's going to be what? Pi times r2 divided by 2, that's a quarter of the circumference around the pulley, plus 2y, that takes care of this distance here plus that distance there, plus then I have to go halfway around this pulley, pi times r1, plus, and then I have this constant length up there, beta. Okay. And what I'm going to do is I'm going to differentiate this thing. And when I differentiate this thing, the length of that rope or cable is going to be constant. We're not yet dealing with something that stretches, or we're going to say that it doesn't stretch appreciably, which is fairly real life. If you get a properly sized cable, it may only, or certainly a chain's not going to stretch very much in relationship to the other dimensions. So the length would be constant, so I'd come up with 0 is equal to x dot plus, we said the distance around this pulley here, a quarter of that pulley, that should remain constant too, shouldn't it? So I mean, this is a constant, this is a constant. I guess if this is C1, this is C2. While we're doing this, this would be C3, and for that matter, B is a constant, C4, isn't it? So I'm really going to then just end up with plus 2 times y dot. So a lot of times when I go through this, if I were to talk about the length of this, I'm not going to mess around with the circumferences. I just say that the length is equal to x plus 2y plus some constant. I just group all the constants together, right? I mean, this will be the one and only time I go through this accounting. But if I were to differentiate this, I still get 0 is equal to x dot plus 2y dot, right? When you take the derivative of the constant, you get 0. Okay. Well, that's kind of nice. I've got an expression with the velocity there. Those are the velocities. And if I differentiate again, I could say that 0 is equal to x double dot plus 2y double dot. So I have then an expression for velocity. I could say that the velocity of A, that's going to be minus x dot, isn't it? You might say, well, how did we get to labeling the velocity of A as minus x dot? Well, as x gets smaller, that's the velocity of A, right? So that's why the velocity of A is minus x dot. What about the velocity of B? Is that y dot? Yeah, because as y gets larger, as B moves down. So as B is moving down here, y is getting larger, whereas as the package A moves to the right, x is getting smaller. That's what that negative is about. So if you make that substitution in here, you can say the velocity of A is equal to 2 times the velocity of B. Some of you that have messed around with pulleys and whatnot probably recognize that fairly easily. And likewise, we could say that the acceleration of A, maybe I'd better use an uppercase to be consistent. There's the acceleration of A and B. The acceleration of A is equal to 2 times the acceleration of B. So we come up with these relationships pretty quick, and the way we do that is looking at the length of that rope. Well, let me try a bit more involved problem. And it's more involved because it actually has, and we'll have to go through it, some people probably can't see it very well, but it has 2 ropes or cables. There's going to be this one here. Maybe I'll put some dots around this. There's that rope or cable, and then there is this one, isn't it? And I'll put some X's on that. So I have 2 separate ropes or cables in that. So as I go through this, and I want to talk about maybe the length of A, I could talk about this dotted one. We'll say that's the length of A. What would that be equal to? No, that's probably not. I should probably take that as the, let's see, if I'm going to talk about the length of A, I should probably take that as the X one, shouldn't I? Okay. So what's that going to be? Y sub A, so that's that distance, plus 2 y sub D, so I have that distance and that distance, plus a constant, right? So there's y sub A. There's y sub D. I've got 2 of those. And then I have this constant piece here around that pulley and around that pulley. So I've got the constant. Now if I talk about the length B, that would be the dashed one. So talking about length B, what would that be equal to? Well, y sub B plus y sub C plus the quantity y sub C minus y sub D. Does that work? I got y sub B here, and then I've got y sub C there, and then I need to deal with this little distance right there, which is going to be y sub C minus y sub D, and of course a constant, C2. So if I differentiate these things, differentiating them, I would have that 0 is equal to y sub A dot plus 2y sub d dot. And I could differentiate again. 0 is equal to y sub a double dot plus 2y sub d double dot. So that's for this equation, isn't it? And if I do this other equation, what am I going to have? So this is L sub A. So what do I have for L sub B? I would have 0. 0 is equal to what? Y sub B dot plus, what am I going to have? 2y sub c dot minus y sub d dot. Doesn't mean you could write this as y sub b plus y sub c plus y sub c minus y sub d. And if I differentiate this again, 0 is equal to y sub b double dot plus 2y sub c double dot minus y sub d double dot. So I got expressions for velocity and acceleration on either one. We notice that both of them have y sub d, so I'd like to eliminate y sub d. So I'd probably solve one of these things for y sub d and substitute it into the other one. And when you do that, you'd come up with y sub a plus 2 y sub b dot plus 4 y sub c dot is equal to 0. So I'm just combining these two equations to get rid of y sub d. Likewise, if I combine these two, I could say that y sub a double dot plus 2 y sub b double dot plus 4 y sub c double dot is equal to 0. 2 y dot sub. Oh, right here. Oh, where did I get this one?
The part you just did, you have y sub a plus 2y sub b plus 4y sub c should be y sub a plus y sub b plus y sub d.
Oh, you're wondering where this 2 comes from?
Yeah.
Okay. So if I solve for this first equation, well, let me grab a piece of paper here. So I'll just take this first equation here and solve this one for y sub d. So I'm going to say that y sub d, well, actually, I think what I will do is I'm going to take the second equation and solve for y sub d. So I've got 0 is equal to y sub b plus 2y sub c dot minus y sub d dot. So y sub d turns out, or dot turns out to be y sub b dot plus 2y sub c dot. Okay with that? So then I substitute that in to 0 is equal to y sub a dot plus 2y sub d dot. And we get 0 is equal to y sub a dot plus 2 times y sub d. So I'm going to have 2y sub b dot plus, then I get that 4 y sub, this should have been c, shouldn't it? Y sub c dot. Is that what we got? Yeah. Good? Are we okay now? Okay. A couple things to talk about this one. We might say that this has 2 degrees of freedom. Two degrees of freedom, because if you give me any 2 of the values, I can predict the other one. So we'd have 2 degree of freedom. It has 2 cables. so it should not surprise us that it has 2 degrees of freedom. This problem here, the previous one that we did, had one cable, has 1 degree of freedom. If you give me either VA, I can predict VB, or if you give me VB, I can predict VA, right? So we'd have 1 degree of freedom here, 2 degrees of freedom here. Well, let's take one of these problems to a numerical end. We've talked conceptually about a couple of them. I'd like to look at this one. It's a nice balance between those two problems in that there's a little more complicated cable system, but there's only one cable. So I'm only going to have one length on this thing. I guess for completeness sake, if we're given the velocity of A going down, we'd like to find the velocity of B. Probably going up. Most people would recognize that. Let's see if the math proves that. If I look at the length of this thing, what am I going to have? Well, YB is from this datum. And we might talk about taking the datum. You can take the datum any place that you want, your reference. It's a lot easier if you take a fixed point. Could you take your reference here at this pulley? Yeah, you could, but it's moving. That's going to make life way tougher. So I would take your reference at a fixed point. Could you take the reference up here? Yeah, you'd get the same equation. It's just going to differ by a constant, right? If you took the reference down here, would it work? Yes, but it's way more difficult to do with a moving reference. Okay, so let me take my reference here, reference everything off of that. And if I were to talk about the length here, I really have 1, 2, 3 of those. So I'm going to say that I have 3 y sub b. And some people might say, well, hey, these two don't go clear to the top. And I would reply to that, okay, subtract a constant, right? Okay. So I think I can take care of that. And what am I going to have to add to this? 2 y sub a, right? And now I've got all kinds of constants. I've got some negative constants here. I have this constant horizontally across here. I've got around the pulleys and whatnot. So let me put that as c. So that would be my expression. When I differentiate this, I come up with 0 is equal to 3 y sub b dot plus 2 y sub a dot. Do we know what y sub a is? Yeah, 0.3 meters per second, right? So what's y sub b? What's this thing? Well, it's really, what, minus v sub b, isn't it? Where'd the negative come from? Well, as this y sub a was getting longer, it was going in this direction, right? What's happening over here? Y sub b is getting shorter, isn't it? So that's where that negative sign comes from. So I can come up with 0 is equal to 3 times minus vb plus 2 times 0.3. So VB turns out to be equal to 0.2 meters per second. And sometimes this negative sign is a little bit difficult. The one thing, if you forget that, you're going to end up with the rope, these two moving in the same direction. Does that seem reasonable? Not unless the rope's made out of something really stretchy. Okay. Yes?
So does this mean, conceptually speaking, that you take all of that stuff, things like the length of that wire on the top and the radius of the pulleys and all that, so all of that is inconsequential for the velocity?
Yeah, so your question that if I look at all of these constant dimensions, they're inconsequential for both the velocity and the acceleration. Yeah, it's because they remain constant. It's because this distance along here is not going to change, that this distance along the pulley is not going to change, that's not going to change, that in fact this distance is not going to change, and around the rest of the pulleys. Yeah. And mathematically, when you differentiate a constant, it goes to 0. Well, so going back and trying to ask questions about this equation here, how did I get 3yb? Well, there's 1yb. there's another YB, and there's another YB. And you might say, well, shouldn't this one, I mean, if I were to have a more careful accounting of what's going on over here, wouldn't this be YB plus YB minus some constant plus YB minus, I guess, the same constant? I mean, that would be that distance if we were more rigorous, right? What happens to those constants? They go away. Other questions? Let's finish up with the last problem that brings another complexity in here. So we have a situation where a farmer or something's trying to hoist a bale up into the barn or something like that. And we have this this angle that's changing. I mean, if we want to put this angle in here, we've got that angle there that's changing. You could imagine as the farmer gets out here, that angle is going to get larger and larger. As the farmer is fairly close to where the bale is being lifted, that angle is really quite small. So we've got some geometry here. We've got the height of the barn where the pulley is attached. That's H. We've got the height of the bale measured from the ground. That's Y. We've got the distance X that the farmer's tractor is from this arrangement. We're told that the farmer's got some velocity A for his tractor, and we'd like to find what the velocity of the bale is. Okay. This is going to be kind of neat because it's going to change with velocity. All these other problems like this one, it was a constant number, fixed number. But here, it's going to be a function of the position. Well, let me put an intermediate variable in here. I don't want to have L show up in my equations at the end, but for an intermediate step, I think it will be helpful. So I'm going to talk about the length of the cable the farmer had to buy. That's going to be equal to 2 times the distance H minus Y. Is that right? H minus Y. Yep, 2 of those, plus L. And like I said, I don't want L showing up in my equation, so now I got to figure out what L is, lowercase l. So I could say that this is, and maybe I'll put the, be real careful here, constant. So I have 2 times H minus Y, and how could I better describe L? Well, I've got a triangle here, don't I? I mean, Pythagoras would say that that's what? Square root of x squared plus h squared? We good with that? Okay. Some people would say we got the L out of there, but that's cheap humor. So, okay. Doesn't get much worse than that. So I differentiate this thing. 0 is equal to, let's see, what I'm going to have. Remember that the height h, that's a constant, isn't it? So I'm going to have minus 2 times y dot plus, then maybe I have to go back to Math 251. What's the derivative with respect to time of h squared plus x squared? To the 1/2. That's the square root, right? So I take the put the power down there, and then I have h squared minus x squared to the minus 1/2, and then I have to go inside that, don't I? I'll have 2x dx dt. So we had to combine how to take the derivative of something that's to a power. Let's see. Yeah, do I have? I think I just messed this up. This is, if this is positive, then this is positive. Yeah. I think we're good now. So this whole thing would be positive. Okay, and I got a positive up here. So this is negative and that's negative. So if I take my conclusion over here, I should have what? This is going to be, the 2's are going to cancel in this thing. The 2 and the 1/2. This x, I'll have an x, and what's dx dt? X dot, thank you. So I could write this as plus x times x dot. So that's taking care of the x. the 2.5 canceled. I got the x dot. And then I'm going to put this in the denominator. Remember that negative power, we could just write that in the denominator as a square root. And maybe I'll keep a consistent order here, x squared plus h squared. Constant goes to 0. So I've got something like that. So now if I make the substitution, what is x dot? That's the velocity of A, isn't it? And what is y dot? That's the velocity of B, isn't it? Okay, so when I move that to the other side and divide by 2, I can say that the velocity of B, moving this piece to the other side, gets rid of the negative sign, is going to be equal to 1/2. I had to take care of the 2 times x times the velocity of A, making that substitution, divided by the square root of x squared plus h squared. So it's a more complicated function for the velocity. A little bit hard to see what that is doing, so I put it into an algebra system. You could throw it in your calculator if you wanted to. This problem's been around for a while. I put it in Maple, so it's been a long time since we've done Maple, but you can recognize Maple. You can recognize, if you can recognize MATLAB, you can kind of see Maple. I just took the height of the barn as 60 feet. I took the velocity of the tractor as 5 feet per second. I've got my expression here, which you recognize, that's the expression if we were to substitute those numbers in. And then we get the plot here. So as the x position increases, as this farmer gets further and further away from the barn, the velocity starts going to what? Looks like it's going to about half of this, right? If I take 5 and divide it by 2, I have 2.5, don't I? Let me extend that out a bit further. So we'll send the farmer halfway to town with this one. So this is the velocity of the bale there, and you can see it definitely went to 2.5, which makes sense, right? I mean, as this farmer gets further and further away from this, it would be very much like you're pulling on it like that, wouldn't it? Which would be an easy problem. That would go back to the first problem we introduced this with, and you'd say, oh, well, that's easy. It's just half of that, wouldn't it? So it should not surprise us that it goes asymptotically to 2.5, or half of that 5 that we assumed. Questions with that? That's actually a good stopping point. We've finished up chapter 12. We sit ready to move into chapter 13. We'll do that next time we're in lecture. Tomorrow when we're in lab, I'll be dedicated to just doing homework problems. So bring your questions. We'll see you then.